So, I'm sure most of us are familiar with the Frank's Red Hot commercials, which advertise certain celebrities putting that stuff on everything. That stuff being Frank's Red Hot sauce, which is something I do quite often. I absolutely love spicy food. Wings, fish, fries. If it has spice, I'll eat it. Which is kind of why I was curious, what makes me want to put that stuff on everything? So, the answer came down to a couple different things, which could be hot sauce, it could be pain relieving patches, or it could be pesticides. What do all these have in common? Capsaicin. So, capsaicin is this molecule pictured here. It's an organic molecule found in most hot pepper plants, which was evolved as a method to defend themselves against predators. As it is a chemical irritant, humans are just weird and like to consume it. So in terms of functional groups from a chemical side, the main things we'll be focusing on in this presentation are this amide group, the aromatic ring here, as well as just this long carbon chain in general with the alkene bond. There's also methyl groups, oxide groups, and a carbonyl. The carbonyl will come in more importance towards the end. So what we're going to mainly be looking at in this presentation is how it applies from a biological standpoint. So, as many of you may know, capsaicin is a chemical irritant. Spicy food tastes spicy because your body thinks it's a toxin, which in a sense it is. The other main thing everybody knows about spicy food really is it has a very distinct scent. You can walk into any of the dining halls on campus, and if somebody has hot sauce out, you smell it instantly. Some people can think it smells very good, other people not so much. I'm one of those people that loves the smell of hot sauce. So we'll get into how these work here. So what we're going to talk about here is why is it spicy? And if you've ever eaten hot food, you'll notice that that painful sensation does not go away. It will linger for minutes, which actually has a very interesting property of capsaicin that allows for this to happen. And lastly, in terms of biology, we'll be talking about how the molecule interacts with smell receptors to make it smell good. Because we have these same pain receptors under our skin that we do in our mouth, but we don't have the other enzymes or other sensations to kind of dull it. So, here we just have an illustration of how the smell receptor works. So instead of focusing on this plug and chain, what I like to call like the bathtub mechanism, where you're plugging a hole, this time it's more of just this amide group and your smell receptor. So if you walk into a room and you smell spicy food, as soon as you walk out of it, it doesn't linger. So you can walk into the dining hall, maybe they have, I don't know, hot chicken one day. You walk in, you smell it, ooh, that smells good. And then you walk out, you don't smell it anymore. So what's happening here is this amide group is going to interact with the smell receptor in your nose, which I've illustrated as this green cylinder. So amide group is the blue part. That's going to interact with it. It will go into the smell receptor, activate it. It will send out neurotransmitters, which will either tell your brain, we need to get out of here because there's poison in the air, which again, kind of true, or it will tell your brain, hey, let's stick around, this smells like good food, this is something we should eat. Everybody's different. This has to do more with psychology than biology and chemistry, but that's for a different presentation. So after you smell it, the smell receptor will detach. Again, there's no plug on it, it's just in, out. And once the smell receptor is empty, it doesn't send off any more signals, which is why your brain stops saying, ooh, we need to go find this food, or we need to get out of here, because it's no longer getting signals from the smell receptor. So if we put acetic acid or vinegar on it, we can lyse capsaicin. So if you'll ever notice, like most weaker hot sauces, your Frank's Red Hot, Cholula, something like the Louisiana hot sauces will have vinegar added or have high vinegar content, and that's because it's going to decrease the strength of capsaicin. Whereas if you eat like the try-hard hot pepper sauces that you buy from like gift shops or whatever, those aren't going to have a whole lot of vinegar, and it's mostly going to be pepper extract. So if we can get into the mechanism right here. So this is just a simple hydrolysis. How this is going to work is we'll protonate this oxygen on the carbonyl. A water molecule will come in here. We'll break the bond between the nitrogen and the carbonyl. This nitrogen will protonate with one of the waters from underneath, and we are left with this benzene with the amide or amine is called vanillamine. It's super common in most plants, which is why you don't really see animals making capsaicin. You can't go cook up a steak and it won't taste like hot sauce. But if you grill peppers, it tastes like peppers because there's capsaicin from this vanillamine compound. And then we just get this long carbon chain with our carbonyl and our alcohol group. So if we move on, so like I just said, plants will make capsaicin. It originally was thought it was just a byproduct of normal plant function, and that plants didn't really want to make this compound because it was toxic to humans, so they thought it was toxic to plants. But in reality, plants made this as a way to defend against predators. If you'll notice, like if you have a garden, if you put jalapeno plants, most small like rodents and birds will stay away from the jalapeno plants because they know that it's an irritant, it's a toxin. So how these plants make it's a really simple reaction. It's just the reverse of what we just showed. It's a simple nucleophilic substitution. This one does not need to be acid catalyzed because we are getting an amine group instead of taking off an amine group, which you'll remember from lectures is very hard to do. So this is just the simple synthesis. So we'll deprotonate our nitrogen, which that then becomes a good attacking group. This will attack the carbon on the carbonyl. Sometimes you could show this oxygen being protonated. In plants, I believe that does happen. But we attack the carbonyl, we get our tetrahedral intermediate. Our electrons will come down, we'll reestablish our carbonyl, and this alcohol group will protonate it, turning into a water. And water is a great leaving group, so it goes away, and we're left with capsaicin. So we take our vanillamine, we take our carbon chain, we do a nucleophilic substitution at a carbonyl, and we're left with capsaicin and water. Lastly, these are the references I used for this project. If you have any questions, feel free to leave it in the comments below. I'll probably be answering these over the next couple weeks. And thank you for watching. Be sure to like and subscribe.